All things were made, this is from John 1 again. All things were made through him, talking about Christ, and without him nothing was made that was made. Since the sixth day of creation, no new matter or energy is being created or destroyed, as the first law states. The first law is the law of creation, and it's tied to an historical event of the creation in Genesis 1 and 2. Isn't that interesting? Do they think that this was history? No. Throw it out. What do you have? You don't have a law. No explanation of why matter and energy is always conserved. No explanation at all. But we know it's tied to an event that took place not very long ago. A historical event described in the Scriptures, in the section of Scriptures that they laugh at the most as saying not being historically and scientifically correct. Well, they just cut off their nose to spite their face. The natural realm, let's look at the natural realm after the creation. This is after the law is implemented, and go back and take some of the things out of this Genesis account so we understand what the world was like then. We have the waters above, and that's where this question of what's the firmament talking about. Let's look at the waters above. The waters above, thus God made the firmament and divided the waters which were under the firmament from the waters which were above the firmament, and it was so. The firmament, and I take it to be atmosphere, divides the waters below from the waters above. You remember in the flood of Noah, what happened? There are two sources of water. It says the fountains of the deep burst forth. You know, there wasn't any rain before the flood. And it says it's watered by a mist that came up, artesian. Well, those broke open, and it's what it said, the windows of the heavens opened up and it flooded the earth. And we're going to see later that the earth, there was a flood later, and that it inundated the earth. But where are the waters above today? These were above that, and they were in a stable state. And if you look at our atmosphere, I would say the firmament in the atmosphere divides the waters below from the waters above. And it says the birds fly across the face of the firmament. Well, that's not outer space. It's got to be above the waters below someplace, and the birds have to fly across the face of it. The water canopy, I take it as a water canopy, the waters above, probably as a vapor, would surround the earth above the atmosphere. And they probably supplied this second source of water for the flood. They don't exist anymore, in other words. But in this original creation it was. And some people say, well, and we'll get into that a little bit. As you go up from the temperature of the earth, straight up from us, the temperature is about 50 to 60 below at 6 miles up, below Fahrenheit. And if you know anything, and the winds are more than 30 miles an hour, and there's an old saying that 30 degrees below, at 30 miles an hour, flesh freezes in 30 seconds. In other words, you wouldn't survive even 30 seconds up there. But here at this surface, we are 80 degrees today. Up there, it's 50 below. But then as you go up above that, it goes up to 1,300 degrees above our atmosphere. You can hold a lot of water in that. Other effects of the waters above. If you had a canopy, okay, like this, a water canopy around the earth, several things are going to be happening. You have a uniform temperature and climate over the whole earth. You have the same temperature at your poles that you have at your equator. And people say, well, why is that? We have the case of Venus. It has a canopy. Now, its canopy is heavier than the Earth's. It's 100 times heavier, in fact. And it has uniform temperatures. And even Venus doesn't rotate. It's locked to the sun, like our moon is locked to us. So it doesn't turn every 24 hours like we do. But even negating that, it has the same temperatures at the poles that it has at the equator, because it's got a canopy. The radiation comes in and is spread out so that you have uniform temperatures all over the whole surface of the planet. This would happen with the Earth if it had such a canopy. So your temperature at the equator would be the same as at the Arctic or Antarctic. That's not the case today, but we don't have a canopy today. But we have real cases. What I'm saying is we have real cases of real planets that are near us, so we know that what can take place. Index fossils. of all the sedimentary layers, except the recent ones, show a uniform, global uniform temperatures. In other words, if I take fossils from, say, the Precambrian layer, as these layers are built up, okay, they have index fossils, fossils that you find as the majority in these layers. They're the same whether they're in Antarctica, Arctica, or the equator, and shows that they grew in the same environment, whether plants or animals. They're uniform, every layer except for the last one, the Pleistocene, the Ice Age. That's where you show polar situations. There are no polar regions in all the other fossils, in the index fossils. There would be no rain from weather fronts if you had a uniform temperature, because you don't have weather fronts colliding. There's no temperature differences, and there's no temperature zones resulting in no rain, just like Genesis 2:5 says. There's no rain, but you won't have rain because you don't have temperature zones, and you don't have the collision of these temperature zones, which is what really causes rain. You have a lot of moisture at a high temperature that hits a cold temperature, and it drops out, drops below the dew point. Other effects of the canopies above. You have a moderate reflection of solar radiation. That's why Venus is so bright. It reflects most of the radiation that comes there because it's got a dense atmosphere and pushes it out. This canopy up there would reflect a lot of radiation. It wouldn't get through, but it then also, that did get through would maintain a moderate greenhouse effect. That would provide mild tropical climates, which is what we find in the fossils of almost every layer. Mild, tropical, semi-tropical, even in Antarctica and Arctica. It'll give abundant plant life at both poles and the equator. The warmer things are and the more moderate they are, the more growth you have. You have to have moisture, but you have to have a moderate zones. The water canopy would protect from strong solar radiation also. I don't know if you know it, but water is one of the best absorbents of radiation. In fact, you can go into a nuclear power pile that they used to have, even up at the University of Kansas. They still, I think, have one at Kansas State. And you can look down into the water and see that radiation glowing down there. But it doesn't hurt you. It never gets to you because it's absorbed by the water. The hydrogen in water is a tremendous absorbent. So this canopy would absorb a lot of the high forms of radiation coming in. It won't get through it. It'll be visible, but the higher forms, X-rays, higher ultraviolets, and even up in the gamma and cosmic rays have a lot more harder time getting through. So you'll have less what? DNA damage. Your genetics are not as damaged. You won't have cancers and that type of stuff. You have longer life for plants and animals as a consequence because their genetic code. One of the reasons we die is because of the aging of our genetic code. And that's why people that have children that are older have sticky genes, because their genetic code has been damaged by radiation and environmental reasons. Other effects from this, you'll have an atmospheric pressure in the pre-Earth would be higher because you're putting more moisture up there. The whole column gets heavier, just like in Venus, it's 100 times ours. Our atmosphere is 1 bar. Theirs is 95 bars on Venus. And putting this moisture up there will push this down and make it heavier here. Now, that will it's caused by the weight of the waters above. Venus is a good example of what that does. In fact, it's so thick in Venus, you know what the pressure on the surface of Venus is? Ours is 14.5 pounds per square inch. There it's almost 1,500 pounds per square inch. That's the pressure of a hydraulic system. And I mean, if you got a hose and run your hand across that and it was escaping from it, it'll inject you with hydraulic fluid. It's that heavier. You feel like walking around on Venus like you're walking through the bottom of the ocean, really. It's thick and heavy. You'll have giants in plants and animals could exist with a higher pressure atmosphere. With the way they call it hyperbaric higher pressure atmosphere would allow for higher metabolism. You know, take any of you. You run the mile here and then try and run it on the top of Pikes Peak. What happens? You're the same person, but you don't have the metabolism up there. But if you increase that pressure and that oxygen coming in, you're in great shape. You can run twice as far. If they put you on an oxygen bottle, you can really pump her out. Also, it would lead to denser air for the flight of larger animals. The pterodactyls and others, they're huge, huge flying reptiles. They can't fly in today's atmosphere. There's not enough air. In fact, as many people know, a helicopter can only go up to about 18,000 feet. It runs out of air. Not for its engines, but for its props. It can't push, there's not enough air to push down. And birds can only fly so high. They can't fly at 30,000 feet. There's not enough air to get wing support. The only reason these airplanes can fly at that is because they're going along at 600 miles an hour and increases your efficiency of your aerodynamics. So two things will take place. You can get giant animals because you got more lung capacity, and also and birds can fly because they've got more dense air. For instance, in the present atmosphere, we can only support probably a 6-ton elephant is the largest animal that we can support. You can take a whale which breathes air, put it out on the land, it'll die because its lung capacity is not big enough. It'll simply die from its own weight. But if you have higher densities, then you can get bigger animals because your lung capacity goes up as a square, but your volume of your body goes up as the cube. And you just run out of oxygen to keep your metabolism going. And that's why also you don't find big animals up at high altitudes. You don't find elephants running around on the top of Mount Everest. Things like that. There's not enough capacity. So you get two things. You get higher metabolism. You also get a better flight.